When numbers are squared, do they feel more complete or just boxed in?
Hello everybody and welcome back to Maths, your grooviest math YouTube channel on the platform. So in the last lecture we discussed expression trees and we saw these were a nice visual way that we could look at, well, how to evaluate an expression. It kind of allowed us to look at the order of operations in a nice clear way where we just kind of followed the tree and we were able to solve the expression. If you aren't sure about that, please go back and watch the video on expression trees because this is going to be a direct sequel to that. So today we're going to be looking a little bit more at some properties of expression trees and how they can give us some more insight into expressions that we didn't have before.
The depth of an expression tree.
So we're going to start right off the gate with just a definition. So this is a new term. So the depth of an expression tree is the length of the longest path from a number to the top operation node. So to clarify what this means, let's just get right into an example. So if we consider what the depth of this tree is, it says it's the length of the longest path from a number to the top operation node. All right, so the top operation node, that's this minus sign right here. And we're looking at the longest path from a number to there. We've got three different options. We can start at 1, and the distance there, that's going to be basically counting the amount of edges we have. So we could go 1, 2, or if we started at 2, we would have 1 and 2 again. Or if we started at 3, we would have a path of length 1 going from this number to the top operation node. But we see here that the longest path, that is going to be 2. So the longest path is of length 2, which then means that the depth of this tree is going to be 2. So we say that this expression tree has a depth of 2. We're just thinking about what the longest path is from a number to the top, or since we're kind of drawing these trees like this, even though this path is of length 1, we're making this edge a lot longer, right? Because we're kind of trying to segment it where we've got these rows, right? So the first row, that has our numbers, and then the second row has kind of like our first wave of calculations that need to be done before we go into the calculations in the second row, and so on. So we can also kind of think of it as how many rows of operations we have, right? So the numbers aren't operations, but the plus and the minus, these occupy two different rows, so this also kind of corresponds to the depth. So the way the tree is laid out gives a pretty visual look at what the depth is. So let's do another example. Okay, so let's look at this expression tree here, and we want to figure out what the depth of it is. So again, we can kind of just consider the amount of rows there are. So the amount of rows of operations, we've got this first row here, we have this second row, and this third row. So the way the tree is laid out, it looks like the depth is probably going to be 3. But if we directly use the definition of depth, it's the length of the longest path from a number to the top operation node. So if we just kind of look at the lengths of these paths, if we start at 8, we get a path of length 1, 2, 3, right? Because there's 3 edges that connect 8 to the top operation node. Similarly, 7, 3, and 5 will also all be of length 3. 6, however, only has a path of length 1 to the top operation node. But since we want the longest path, this depth is going to be 3. All right, so it's not too difficult of a definition, right? It's quite visually baked in to the expression tree itself. Let's just do one more example to get kind of a hang for these, and then we're going to talk a little bit more about why we even care about the depth of an expression tree. So this is kind of an easy one, but what do you think the depth of this tree is? It's going to be 1, right? Both of these have a path of length 1, so that's the longest path. It's the only path. So the depth of this tree is 1.
Evaluation steps.
So let's just take a quick break from trees and we're going to tie it into this concept in just a moment, but let's talk about evaluation steps. So when we evaluate an expression, we do it in steps. So for example, if I take the expression 3 plus 4 times 11, well, there's 2 steps I'm going to do in this. The first thing I do is the multiplication, right? Just following order of operations, so I get 3 plus 44. And then the next step afterwards is I add the 3, and I get 47. So this expression was evaluated in two different steps, right? First to do the multiplication, which was necessary to do before we could do the addition, right? However, we have seen that sometimes in a single evaluation step, multiple independent computations can be done. So for example, if I have, let's say, 2 times 3 plus 4 times 5, in this situation, I have the 2 times 3 and I have the 4 times 5. Those both have to be done before they get added, but neither of these individual products actually have any influence on each other. We would say that they're independent of each other. So because that's the case, we can calculate these multiplications in the first step, in the same step, right? So we can do the 2 times 3 to give us 6, and the 4 times 5 to give us 20, and then in the next step, we can do the 6 plus the 20 to get 26. But it's important here to note that because these are independent calculations of each other, they could be done in the same step. Whereas up here, the plus and the multiplication weren't independent because we had to do the multiplication before we added this 3 onto it. If we did the addition first and then multiply next, we'd get a different result, right? So let's look at these in the context of trees. So if we take the first one, the 3 plus 4 times 11, this looks like this. So we do 4 times 11 first, and then we add the 3, right? And we see baked into the structure of this tree, absolutely cooked in there, is we have the multiplication has to be evaluated before we do the addition, right? Now let's look at this other one where we have 2 times 3 plus 4 times 5. So before we do the addition, we have to evaluate the multiplications, but notice something. These multiplications, we see their trees are completely disconnected from each other, right? This subtree is completely disconnected from this subtree. And that reflects the fact that we can essentially evaluate these two products independently of each other so they can be done in the same step. And this is also seen in the tree where when we kind of think about the rows that the operation is on, these operations are on the same row, which means that they can essentially be done in the same step. Now this is where the depth of the tree comes in. The depth of the tree we know basically corresponds to these rows of operation, which is going to correspond to how many steps an expression can be evaluated in. So notice, both of these trees have depth 2, right? And notice, both of them were evaluated in 2 steps, right? Because we were able to do these 2 calculations independently, we were able to evaluate this tree in 2 steps, and this tree we had to do in 2 steps as well. So both of them have a depth of 2, which meant we were able to evaluate them in 2 steps, and that's the key point of this video. The depth of an expression tree tells us how many steps that we can evaluate an expression in. So this is a very interesting property about expression trees where they tell us something more about the expression, not just how to evaluate the expression, but in what time or how many steps we can evaluate the expression within. So let's maybe do some examples. So it says, how many steps can 3 squared plus 5 times 7 be evaluated in? All right, so if we make the expression tree for this, we get that 3 squared, that's going to be 3 to the power of 2, 5 times 7, we're going to use a multiplication node, and then we add the 2 afterwards, right? So this is an expression tree that we can make for this. And since 3 squared and 5 times 7 are independent, that means they can be evaluated in the same step. But we see that the depth of this tree, right, the longest path from the number to the top node is going to be 2. So the depth is 2. So it can be evaluated in 2 steps. Right, we do the exponentiation and the multiplication in the same step, and then we take those results and we add them in the second step. So if I asked how many steps can 3 plus 4 plus 5 plus 6 plus 7 be evaluated in? Well, we just have to start by making the tree. So we have 3, 4, 5, 6, and 7. So this expression tree represents this expression here, right? We're just adding all of these values together, kind of adding it in one step at a time. And if we do that, what's the depth of this tree going to be? Well, the depth is going to be the longest path, which is going to be starting from the 3, right? These other ones are going to have shorter paths. So let's start from the 3. We're going to have 1, 2, 3, 4. So the depth is 4. which means it can be solved in 4 steps. However, there's something not quite great about this. Yes, what we did is correct. However, I can make a different tree for the same problem. So, for example, I could do 3 plus 4, 5 plus 6. So I could do something like this instead, where I do the 3 plus 4 and the 5 plus 6, I add them up in the same step, and then I continue to add everything else. But this gives me the same result, right? We're ultimately just adding all of these numbers together. We're just kind of choosing how to add them, right? In this case, we're going to be doing the 3 plus 4 and the 5 plus 6 in the same step, and then we're just going to add everything else afterwards. But this gives us a different depth. This gives us a depth of 3, right? Right? Length of 1, 2, 3. So this gives us a depth of 3, which means that this can be solved in actually 3 steps. So now the question is, which is it? Is the depth 4 or is the depth 3? Can it be solved in 4 steps or 3 steps? And the answer is, well, yes, it can be done in both ways. It just represents 2 different ways of evaluating the same expression that give us the same result. We could evaluate the expression this way, where we basically just add one piece at a time. We go 3 plus 4 is 7, plus 5 is 12, plus 6 is 18, plus 7 is 25. But over here, what we're doing is we're doing, okay, 3 plus 4 is 7, and 5 plus 6 is 11. So we're doing that kind of in the same step. And then we're adding those together to get 18, and then we're adding that to the 7. So that has less steps because we're just doing it in a different way. So that is something to watch out for, is that just because you get the depth of a tree being something, yes, that's the amount of ways you can solve it using that order specifically, but it is possible to evaluate the expression in a different way. And that could have a different tree, which could have a different depth, which just means that that way will have a different amount of steps that you can solve it in. But we do see that some are better than others, right? This tree is better because it can essentially solve our expression more efficiently. It can be done in less steps. We have to write a smaller number of equal signs, right? So it can be done a little quicker. So now the question is given a tree, are we able to rearrange the tree so that we get a smaller depth?
Rearranging trees.
So we just saw that some expressions can be expressed using different expression trees, just like up here, in which case some had a smaller depth, and thus could be calculated in less steps. The question now is, can we arrange some expression trees to decrease the depth, right? So if we just started with this expression tree here, how would I be able to kind of take this and rearrange it maybe to look something more like that? So this isn't always going to work, and so it's going to be a little bit of a case by case, where just the more practice you get, the more kind of intuition you'll develop as to whether or not you can rearrange the tree to decrease the depth. So for example, if I took something like 6 plus 4 to the power of 3, there's not going to be really anything I can do to rearrange this tree, at least not in a way where I can get a smaller depth, right? I can change the order of the 6 and the 4 because the order of addition doesn't matter, but I'm pretty much stuck after that, right? We have to do the addition and then we have to raise that to the power of 3. Those have to be done in 2 separate steps. So this cannot be rearranged. But an example of something that can be rearranged was something like we had above. And so one thing to look out for with rearranging trees is oftentimes if you have kind of the same expression in a row, that may be a sign that you can rearrange the tree. And this is because oftentimes the operations, in particular for multiplication and for addition, it doesn't matter the order you do it in, right? I could do 3 plus 4 times 5, and that's the same thing as 5 plus 3 plus 4. Or I could do 7 times 8 times 9, and that's the same thing as 8 times 9 times 7, right? So it doesn't matter the order in which we add or which we multiply. So that's often something that we can look out for. So for example, if I do 2 times 3 times 7 times 6, this can be rearranged into looking like doing the 2 times 3 and the 7 times 6 in the same step, and then multiplying those afterwards, right? So our depth decreases from 3 to a depth of 2. And this worked nicely because basically we're just combining everything through multiplication to begin with. So we can definitely reduce some inefficiency there. And we already saw an example for addition, just like above. With subtraction and division, it is possible, but it might be a little trickier. So let's look at a tree where there's several subtraction statements. For example, let's consider something like this. We have 10 minus 3 minus 7 minus 6 minus 5. We've got a lot of subtractions in a row, but the problem is we can't just change the order of subtraction, right? 10 minus 3 is not the same thing as 3 minus 10, right? So we somehow don't have as much flexibility as we did with addition and multiplication. But there is one thing that is interesting to note. When we subtract off a lot of different things like this, right? We know that subtracting is the same as adding a negative, right? So if I do something like 10 minus 3 minus 7 minus 6 minus 5, that's the same thing as me doing 10 plus negative 3 plus negative 7 plus negative 6 plus negative 5, right? And we know that when we add a bunch of negatives, that's basically just us adding the number component or the magnitude of these numbers and then putting the negative on afterwards, right? If there's no positive in there and it's all negatives being added, we just add them up as normal, right? So we would just do basically 3 plus 7 plus 6 plus 5, right? And then we would put a negative on afterwards. And so what this means then is that we can actually kind of write an expression like this to look more like that, where we're taking all the pieces that we're subtracting, right, considering they're all positive, and we're combining them through addition, and since that's basically the whole size that we're subtracting off, we can subtract that off afterwards. So with this in mind now, we can actually rewrite this tree in the following way, where we basically combine all of the pieces we're subtracting off through addition, and then afterwards we subtract that whole result off from the 10, because again, we're trying to subtract all of these values off from the 10. So we're just combining these values first and then subtracting that result from the 10. So this is a rearrangement of the tree, even though it looks quite different. In particular, we've converted some of these subtractions into addition. But we do see now that the depth of this tree is 3, whereas the depth of our original tree was 1, 2, 3, 4. So we did decrease the amount of steps that this calculation can be done in. Granted, it wasn't as obvious to do, so it may have been more worthwhile just to stick with the original calculation, but we're just kind of looking at how can we minimize the calculation steps.
Concluding thoughts.
Okay, so there's more examples that we can go over, but we're going to save that for the exercise video. But I hope you found this video useful. I think it's a really interesting property of these expression trees, and it's something that we weren't really able to see, at least not very clearly, when we were just looking at plain old expressions. So we see expression trees, they have a lot to offer. They give us a visual representation of the order, and they give us a visual representation of how many steps that we can actually do it in, and that's accomplished by looking at the depth of the tree. Furthermore, we saw that sometimes we can express the same expression with different trees, and that can result in a different depth, a different evaluation time, which means that maybe some of these trees are a little better than others. And we saw that sometimes we can rearrange these trees to get us to the more efficient tree ultimately. Hope you found it interesting. Until the next video, you have a good one, you stay groovy, and I'll see you then.
F.O.A. Maths.